Good morning. In the previous lecture, we introduced mathematical induction and we showed how to use it to prove a variety of theorems. In this lecture, we will introduce another form of mathematical induction, strong induction, which can often be used when we cannot easily prove a result using mathematical induction. The difference between mathematical induction and strong induction is in the induction step. For mathematical induction, the inductive step is predicated on proving P of k implies P of k plus 1, whereas strong induction includes the prior statements P of k subscript I such that P of 1 and P of 2 and all of them, P of k implies P of k plus 1. Mathematical induction can be used to prove statements that assert P of n is true for all positive integers n, where P of n is a propositional function. A proof by mathematical induction has two parts: a basis step where we show P of 1 is true, and an inductive step where we show that for all positive integers k, P of k is true, then P of k plus 1 is true. The principle of mathematical induction. To prove P of n is true for all positive integers n, where P of n is a propositional function, we complete two steps. A basis step, we verify that P of 1 is true, and an inductive step, where we show that the conditional statement P of k implies P of k plus 1 is true for all positive integers k. Strong induction. To prove P of n is true for all positive integers n, where P of n is a propositional function, we complete two steps also. A basis step where we verify P of 1 is true, and an inductive step. We show that the conditional statement P of 1 and P of 2 all the way out to P of k implies P of k plus 1 is true for all positive integers k. Example 2. Show that if n is an integer greater than 1, then n can be written as the product of primes. Solution. Let P of n be the proposition that n can be written as the product of primes. Basis step. P of 2 is true because 2 can be written as the product of 1 prime itself. Note that P of 2 is the first case we need to establish. Inductive step. The inductive hypothesis is the assumption that P of j is true for all positive integers j less than or equal to k. That is, the assumption that j can be written as the product of primes whenever j is a positive integer at least 2 and not exceeding k. To complete the inductive step, it must be shown that P of k plus 1 is true under this assumption. That is, that k plus 1 is the product of primes. There are two cases to consider, namely when k plus 1 is a prime and when k plus 1 is composite. If k plus 1 is prime, we immediately see that P of k plus 1 is true. Otherwise, k plus 1 is composite and can be written as the product of two positive integers a and b with 2 less than or equal to a, less than or equal to b, less than or equal to k plus 1. By the inductive hypothesis, both a and b can be written as the product of primes. Thus, if k plus 1 is composite, it can be written as the product of primes, namely those primes in the factorization of both a and those in the factorization of b. Example 4. Prove that every amount of postage of 12 cents or more can be formed using just 4-cent and 5-cent stamps. Solution. We will prove this result using the principle of mathematical induction. Then we will present a proof using strong induction. Let P of n be the statement that postage of n cents can be formed using 4-cent and 5-cent stamps. We begin by using the principle of mathematical induction. Basis step. Postage of 12 cents can be formed by using 3 4-cent stamps. Inductive step. The inductive step is the statement that P of k is true. That is, under this hypothesis, postage of k cents can be formed using 4-cent and 5-cent stamps. To complete the inductive step, we need to show that when we assume P of k is true, then P of k plus 1 is also true, where k is greater than or equal to 12. That is, we need to show that if we form postage of k cents, then we can form postage of k plus 1 cents. To see this, suppose that at least one 4-cent stamp was used to form postage of K plus 1 cents. Then we can replace this stamp with a 5-cent stamp to form postage of K plus 1 cents. But if no 4-cent stamps were used, we can form postage of K cents using only 5-cent stamps. So we can replace 3 5-cent stamps with 4 4-cent stamps to form postage of K plus 1 cents. This completes the inductive step. Now let's do it via strong induction. The basis step. We show that P of 12, P of 13, P of 14, and P of 15 are true. We can form postage of 12, 13, 14, and 15 cents using 3 4-cent stamps, 2 4-cent stamps and 1 5-cent stamp, 1 4-cent stamp and 2 5-cent stamps, and 3 5-cent stamps respectively. This shows that P of 12, P of 13, and P of 14 and P of 15 are true. Inductive step. The inductive hypothesis is the statement that P of j is true for 12 less than or equal to j less than or equal to k, where k is an integer with k greater than or equal to 15. That is, we assume that we can form postage of j cents where 12 is less than or equal to j less than or equal to k. To complete the inductive step, we need to show that under this assumption, P of k plus 1 is true. That is, we can form postage of k plus 1 cents. Using the inductive hypothesis, we can assume that P of k minus 3 is true because k minus 3 is greater than or equal to 12. That is, we can form postage of k minus 3 cents using just 4-cent and 5-cent stamps. To form postage of k plus 1 cents, we need only add another 4-cent stamp to the stamps we use to form postage of k minus 3 cents. That is, we have shown that if the inductive hypothesis is true, then P of k plus 1 is also true. This completes the inductive step.